Okay, what are we going to do here? So as usually a tutorial, some people here might know more than others, and I'll try to present it in a way that will be of interest to all of you, whether you know a little bit about what I'm talking about or whether it's all completely new for you. And since I don't have a clue what you know, I really encourage you to ask questions, okay? And here's what I tell my students: if you think and you don't understand something, and you're shy or hesitate to ask because you're sure that everyone else actually know, they don't. So it's just someone has to ask. Okay, so what we're going to talk about is kind of the very basic question of probability adapted to the particular application that we need in computer science. And we get in a few slides to the question of why we develop independent computer, kind of new probability tools in computer science where probability was already there for many years, and I'll try to answer that question. But basically what we're going to look around is we're going to start with what's called large deviation bound. Now, I assume that some of you know or have used or at least heard of something called the Chernoff bound. Okay? And so if you have never heard about the Chernoff bound, well, it's time that you learn about it. This is probably the most often used tool in analysis of algorithms these days. But if you know about Chernoff bound, what I'm going to show you is that I'm going to give you some kind of a perspective on what is a Chernoff bound. So most of us use Chernoff bound as kind of a black box. Well, if I fit all the requirements, then I can use it, and otherwise don't. I can't. Well, that's not the real thing. Chernoff bound is actually an example of kind of a general scheme called large deviation bound. Chernoff bound became very popular in computer science, but there are other many important variants, which are also used these days, but are less frequent, less known. And just for the fun of it, I listed it as the list of the names of all the bounds. And there's a long history here. By the way, Chernoff did not invent the Chernoff bound. Like it's often in science, the names are not the right name. And even Chernoff himself, someone you can still meet in Boston, he's a retired Harvard professor, not in computer science, by the way, a statistician. He would tell you that it's all a mistake, he never did it, it's not credit to him. It's probably Bernstein, who was back in Russia, probably was the first one to think about this idea. And then there's a whole chain of development which will go one step after the other, which goes to Chernoff and Hovding and Azuma-Hovding and McDermott, and they all have some meaning here. And then I'll show you that there's actually a general recipe here, and if you understand the recipe, then you can use it for many other applications that don't fit into this or that particular one. Okay, so large deviation is about how far is the empirical expectation, the empirical average from the actual expectation of a random variable, which is the basic question you ask in statistics. So I take a few samples. So I want to know what's the average height of a student in IIT. So I measure a random sample, and I take the average, and now I ask, okay, so this is my statistic, or this is the empirical number that I have for my measurement, but there is some real value, the average, and the question is how far they are from each other, okay? That's the basic question in a lot of statistics, and large deviation tries to answer it in various ways. But as we progress now in computer science, and in particular the big success, or one of the biggest success of computer science in recent years, is machine learning. And in machine learning, the question is much more complicated than how far is my sample from the real value, because I often don't really know what am I searching for. And in fact, I want a sample that will be good for many questions simultaneously. Okay? So this fall under, again, many names. We'll refer to it, particularly computer science refer to as the sample complexity. It's also something called uniform convergence. There's many names for this, and it has a long history as well, but became very important in recent computer science. So the second part of what I present here, we'll talk about this sampling complexity. It won't be today. It will take a few hours before we get there. Well, that's kind of high-level tools about what I'd like to cover here. And yeah, I have to make some advertisement. You know, it's America. You have to have commercials. So yeah, it's all part of it is in a book, which some of you might know, and some of it is more recent material, and it will appear in the book that Mike and I finished to write the second edition. But as you know, it takes a year until you actually can see it in a book. So it's all there, and more will be available soon. Okay. So, oh geez, that's dangerous here. Okay, so large deviation bound is kind of a trade-off between, and again, it's the usual trade-off you have in mathematics, where if you give me more conditions in the theorem, I can prove stronger results. So a lot of theorems are about the trade-off between what you have to assume and what can you prove with these assumptions. Okay? So the same game is in the Chernoff bound, in the large deviation. In particular, the most popular, the Chernoff bound, basically talks about independent Bernoulli random variable, independent 0, 1 random variable. So if I take, so basically it asks, how many independent 0, 1 random variables I have to average, or values I have to average, in order to get a good estimate of the actual probability. Since it's 0, 1 random variable, the expectation is the probability. Okay. But now you say, well, okay, life is not only 0, 1 random variable, there are more interesting things. So the first kind of relaxation, we say, well, okay, so what happens if I have independent observation of a random variable, but it's not a 0, 1 random variable? Well, it's not hard to show that if it's completely unbounded, there's nothing you can do. But if the random variable is bounded, then we'll get a bound which handles that one, and this is called the Hoeffding bound. And then comes the real jump when you say, well, okay, do they really need to be independent? So, well, we actually get rid of that as well, well, in some way. And so what we'll do is we'll talk, and I'm sure that this will be new to some of you and not new to some other people, but I'll talk a little bit about something called martingale, which is a sequence of random variables that are not independent, but they have a very structural dependency, and we'll find a way to prove a variation bound or a large deviation bound even for a sequence of random variables that are not independent. And then we'll see that from that one we get very useful results about bounding the deviation of a function of many random variables, and then suddenly it will jump to questions like what's the chromatic number of a random graph, or what's the links of the past. So suddenly we'll get from probability to actually answering concrete questions that seems completely from a different world. Okay, but before we get that, there's this question that I always ask when I give this kind of tutorials, and often when the audience is maybe not like here, but audience that varies from different disciplines. And the obvious question was, well, okay, you're a computer scientist and you think you invented the world, but there were interesting science before computer science, and mathematician, probabilistic researchers already ask all these questions. So why we invent the wheel? Why do we build new theory of probability or probabilistic technique for computer science? And you can have a long answer for that, but the short answer is here. So here is the prototype of a result in statistics or in probability theory. Okay, so you probably recognize it as the central limit theorem. And the central limit theorem basically says, well, if I have n independent, identically distributed random variable with mean mu and variance sigma square, then if I take a lot of observations, so if I take the average of this and normalize it, then what do I show? I show that in the limit, okay, this distribution turned to be normal. Okay, I'm sure you all saw that. Okay, well, that's very nice for theoretical mathematics. Okay, but in computer science, the limit is not enough. I want to know how far do I have to go. So in computer science, we really want to count. We want to count the steps. So each of these samples has a cost. Okay, so in real statistics, it has a cost of I have to go and sample, ask someone a question or measure or something. In computer science, that's computational cost. Okay, so it's very nice to know that in the limit, the deviation, behave like normal distribution. Well, it doesn't help me in real life when you ask me how many samples I really need. Okay? So in computer science, we want to have something that we don't care about the limits. We care about, how far we have to go in order to be sufficiently close to the limit. Okay? Or in other words, this is the standard Chernow bound. We'll get to this in detail, but just to give you a flavor of what we're going to do here and the contrast to the central limit theorem, here we're going to say if I have n independent Bernoulli random variable observation, or observation of Bernoulli random variables, okay, well, if they're identically distributed and the probability of each of them being 1 is pi I, then the probability that the sum of them is far from the sum of the expectation, okay, is going down, okay, according to the expectation of the sum, okay, or if we, maybe better to normalize it to say the probability that the average here is far by delta from the expectation of the random variable, and then we'll get that it goes exponentially, down exponentially with n. Okay? So, in other words, not only where is the limit, but how far do I get to the limit? So that's the big difference between many of the tools we build in computer science and the tools that you use or that you get in standard probability theory. By the way, it's also relevant, we don't talk about it here, but it's also relevant to queuing theory. So in queuing theory, there are beautiful results, but they usually talk about the limit distribution, okay? And then when in real computer science, we want to ask about the size of buffers, the queues in routing and stuff like that, then queuing theory is somewhat limited in answering your question because we want to know, how fast things converge, what happens when they don't converge and stuff like that. Okay, that's a side remark. Okay, so now we're going to ask, okay, so now we're going to start, okay, so this was introduction, now we get to the real stuff. Okay, now everyone in probability is some variation on what's called Markov inequality. Now that's a very interesting phenomenon. Markov inequality on its own is extremely weak bound, which you probably all saw in some class. It's extremely weak bound, but everything is building on it. Okay? So what's a Markov inequality? It only applies to random variable that is non-negative. Okay? And the probability that this random variable is greater than some value A is bounded by the expectation of the random variable divided by this value a. And it's really trivial to prove if you think about the expectation, the expectation of x. Okay, let's assume that it's a discrete random variable, so that's sum of I probability that x equal I. Okay, so now let's do two simplification. First, we'll just look, so this is definitely greater or equal than if we just sum above A. Okay, probability that x, time I probability that x equal I. Okay, but now if we sum only above A, then definitely it's greater than sum of A probability I greater or equal to A probability x equal I. Okay, so now if we take A outside, then what's written here? The probability that x is greater than A. Okay, and we get this. So that's a very simple bound. Okay, and the only reason we mention it here is because everything else we'll build on that bound. And it's amazing that you start with this. We'll show later, we'll do the comparison with other bound. We'll see that this is so weak. But when you build on this, you get amazing strong stuff. Okay, the first one, again, not really what we're talking about here, but the first bound that is built on Markov is Chebyshev inequality. And Chebyshev inequality basically said, well, instead of thinking about x, not thinking about x minus e of x square, and then we plug it in and we get Chebyshev. Okay, and Chebyshev is first for the stronger bound. It works for random variables that are positive and that can be positive and negative. And again, we'll do the comparison. We'll see that it gets better bound. Okay, but that's not strong enough for what we need. We want bounds that goes down exponential. So now we get to this general technique of large deviation bound. Okay, and the technique is the following. I want to know what's the probability that x is greater or equal to A. Okay, well, if I pick t that is greater than 0, then the probability that x is equal to A is the same as the probability that e to the tx is greater than e to the ta. Okay, as long as I took t that is greater than 0. Okay, now we got something very interesting. We started with a random variable that can be positive or negative, but e to that is always positive or now negative. Okay, so now I can take this. Okay, now we have a random variable here that is not negative. And now I can apply Markov inequality. Okay, but Markov inequality now says what's the expectation of this divided by this. Okay, so the probability that this random variable is greater than this is bounded by the expectation of this random variable divided by the value. Okay, so we took a random variable, and instead of asking what's the probability this random variable is greater than A, we ask what's the probability that e to the t to the x, e to the tx of where x is this random variable is greater than e to the ta. Now, if you look at it, that's equality. Okay, so we kind of didn't do anything other than written it in a more complex way. Okay, as it happened, this jump from looking at the random variable, looking at the exponent of the random variable has a very deep meaning that we're going to discuss in a second. And this gives very strong bounds. Okay. Now this is for the question whether x is greater or equal to A. We can answer the opposite question with using t less than 0. So the probability that x is bounded by A, okay, from below, from above, well, now t is negative, so if we multiply t both sides, we switch the inequality, okay, so this is now going to look the same, only now t is negative, okay, and we get the same bound using the Markov inequality, okay. Now I realize for those of you who see it at the first time, this is just symbolic manipulation, and it will take some time until I can show you, the application of this. So bear with me, we have to go through some formalities until we get to the real application, okay? But this is the kind of the general form, okay? So in order to get all these different bounds that we looked before, that we enumerated before, basically what you're doing is you're doing the following. So here is like a recipe, okay? An algorithm for generating bounds, okay? So you take a random variable. The hard part usually is to compute the expectation of e to the tx, okay? And now you get, from what we had before, that the probability that x is greater than a is bounded by this expression, and the probability that x is bounded below by a is this expression. But now we have a free value here to play with, because here we just say, well, take any t, either greater than 0 or lower than 0, smaller than 0, okay? So now you can play with t. And so, of course, we'll try to find the t, since we want to get a bound, we'll try to play with t to find the minimum value for this bound. Okay, so that will be the second step. Now this often gives us kind of hard to remember bounds. So the third one is usually we're simplifying to something that is easy to work with. So all the bounds will have this structure. Okay. But before we get to particular bounds, what I want to show you, and this is often ignored completely in computer science, is that this is not a magic. There is a very particular reason why we move from the random variable to the expectation, to the exponent, to the random variable in the exponent. Okay. So maybe those of you who study enough probability, what's this function? I don't hear. Moment generating function. Okay. So it's not that Chernoff or Hofding or whatever dream about some function or tried a long list of functions. There is a particular reason why we use the exponent of t, of tx. The reason is that this is the moment generating function. And the moment generating function, in a way, encodes the whole distribution. Okay? So Markov inequality, just say, well, give me the expectation, and I'll give you some bound. Chebyshev said, well, give me a little bit more. Give me the variance, and I'll give you a stronger bound. Okay? Now we say, I don't want just the first moment, the second moment. Give me all the moments. Give me the whole distribution. Well, if you give me the whole distribution, I'll give you a much, much stronger bounds. Okay, and I'll show you in a second how strong they are. Okay. So, just to remind you, so the moment generating function is the expectation of e to the tx. Okay, and this is just for those who don't remember. So, the moment generating function, the reason we call it the moment generating function is that in the function, encoded in the function, are all the moments of the random variable. So a moment of the random variable is the expectation. So a moment, so the k moment of a random variable is e of x to the k. Okay? And a very hard theorem to prove that we usually don't do in basic courses is that there is a one-to-one correspondence between a distribution and its sequence of moments. So if you know the sequence, well, if all the moments exist, then knowing the sequence of moment is equivalent to knowing the distribution. You can go from one to the other. Okay, so the moment generating function defines all the moments. So in a way, for the distribution that we work with, or for which all the moments exist, in a way, what you put into the recipe or what you put into the inequality is the full information about the function, about the distribution. Okay. Okay. So how do you do it? Well, if you take the moment generating function, you take the k derivative of it, and you set t to 0, then you get the t moment, the k moment. Okay. The last thing that I want to remind you is that the moment generating function of a sum of random variables is the product of the moment of independent, the sum of independent random variable is the product of the moment generating function. And that's actually very simple, because if you write it, so the moment of x plus y is e to the t x plus y, and if it's independent, then the expectation, you can take the product of the expectation, you get the minimum. We're just going to use it in a second. Okay, so one thing to remember is that it's not a magic that we go to this e to the tx. We're using the moment generating function, and now we expect to get a better, stronger bound. Okay, so here's kind of the proof of the first basic Chernoff bound. So let's x1 to xn be a sequence of independent Bernoulli trial random variables. So the probability x is 1 is pi. The probability that xi is 1 is pi. The probability, and then we're looking at the sum of the xi's. So notice, by the way, that we don't need the x1 to xn to be identically distributed. What we need them to be is 0, 1 random variables, but each of them can have its own probability to be 1. Okay, which I remind you is also its expectation. Okay, so I have a sum. This is actually very important when we get to analyze algorithms, because we often ask, well, how many steps we have to do? Each step has its own probability of success and not. And so if you know, we can still apply the Chernoff bound even if the probabilities are different. So now let's mu be the expectation of the sum. Okay, sum of the expectation, which is the sum of pi's. Okay. So now what we want to ask is, if I take n observation of x1 to xn, and I look at the sum, the value of what I get, how far is it from sigma of pi? Okay, or in other words, if I look at the sum of n observation, how good are they as a predictor for the real expectation? Okay, that's shuffling it as a statistical question. Okay, so we'll try to use this recipe. And the first one is we have to compute the moment generating function, or the expectation of e to the tx. Okay, and that's usually where the difficulty is. Okay. But now we're going to use the fact that x is a sum of independent random variables. Okay, here, sum of independent random variables. Okay. So in that case, we just have to compute the expectation of each xi of e to the txi. Oh, but now it's getting very easy, because xi is just getting the value 0, 1. Okay, so if it's 1, then it's pi e to the t, and if it's 0, it's just 1 minus pi. Okay, so that's easy. And now we do some manipulation here, and it's bounded by e to the pi, e to the t minus 1. Okay. And so now I have a bound for each of the moment generating function of each of the xi's. So I take the product of it, and I get a bound for the sum. Okay, and through all this talk, I'll skip the arithmetics or whatever the symbolic manipulation. It's all on the slides, if not in the book. I want to give you the high-level idea. I don't want to get into the real computation. Okay, so after I computed the moment generating function of each xi, I use the fact that the xi are independent. So the moment generating function of the sum is the product of the moment generating function. Okay? So now I finish one part. Sorry? Mu is the expectation, sigma of pi I. Okay? Just shortcut. Okay. Okay, so now we apply the Markov inequality. So the probability that x is delta away from its expectation. Okay, so it's probability that e to the tx is greater than e t1 plus delta mu. And now it's bounded by the expectation of this random variable divided by the value. Okay, and the expectation we computed is this value, and so we have this bound. Okay. So now we said the last part, second part of the recipe is, well, we have this free value here, t, free variable t, and now we want to optimize with respect to t. We want to get this value as small as possible with respect to t. Okay? So you can take the derivative, or just believe me that if you plug t to be ln of 1 plus delta, and you do some manipulation, you get this bound. Okay? And I have to see that t, I only can plug here t that are greater than 0, but if delta, the deviation, is greater than 0, then t of ln 1 plus delta is greater than 0, and everything is fine. And I get the first version of a Chernoff bound. It looks good, but it's somewhat hard to remember or to memorize. So now come kind of games of how do you take it to look just something that is easier to work with without, giving up too much on a bound. So this is tighter. This is easier to remember. So the probability, and this is what you usually see in papers. So the probability that x deviate by more than delta from its expectation is bounded by the expectation delta square over 3. Okay? And why you get this 3, these are just technicalities of how you show that this is bounded, that this is an upper bound for this. Okay? And then you can get even a weaker bound, but easier to work with, that if you go for a very large variation, so if you go for a variation which is 5 times the expectation, then the probability that you're greater than that value is just 2 to the minus that value. How do you prove it? We won't do the arithmetic here. It's basically high school calculus. So you take the derivative, the second derivative, and you show that you get the right bounds. Okay, so we won't do it here. So basically, you show that, okay. So, for example, you want to show that this is always greater than this one. Okay, so you take the derivative, the second derivative, you do some dirty work, and you get the bound. The same for the other one. Okay, we will not do it in detail, but a similar bound work on the other direction. Okay, so now you ask, what's the probability that your random variable is delta away below the expectation? Okay, so what's the probability that instead of getting the expectation, I got a value that is delta away below that? Okay, and you get basically the same bound. Okay, only here you have 2 instead of 3 technicalities. Okay, and you do it the same way. We already computed the expectation. Okay, so we use the same bound. The only thing is now we have to use a t. In order to minimize, we have to use a t that is greater than, that is smaller than 0, because we switch the order of the inequality, but this is exactly true for this delta that is between 0 and 1, which is what you can plug here. Okay, so let's give you the bonds. Okay. How good are these bonds? Okay, so let's take the simplest one. So assume that I flip a coin, a fair coin, half-half coin, n time. And ask what's the probability that the number of heads, so what's the probability that the number of heads deviate from the expectation by more than this value, half square root 6 n log n. Okay? So now we plug it into the Chernoff bound. So to plug it, we want to, we have to write it a little bit different. We want to ask what's the probability that x is greater than the expectation plus a deviation. Okay? And we look for the one going up above that or below that. Okay? And we get that the probability is 2 over n. Now, how good is this bound? Okay, so now, some intuition behind it. No, don't just take the symbols. So how good is this bound? So if I flip a coin n time, and what I'm saying now is true for any random variable. It doesn't have to be flip a coin, but flipping a coin is a good example. How tight I could actually expect the actual result to be, how far should I expect it to be from the expectation? Okay. I mean, it's definitely very unlikely to be exactly the expectation. Okay, the probability of getting exactly half is very small. Okay, so where you actually expect it to be? Where is most of the mass? Okay, well, that's a standard deviation. Okay, so I cannot expect to prove a bound that is better than plus minus 1 or 2 standard deviation, because it's just not true. With high probability, it's somewhat distributed in plus minus 1 or 2 standard deviation. You cannot prove stronger bound than that. Okay? What's the standard deviation here? The standard deviation here is square root of n. Okay? Some constant around. Okay? And then the ln here is what gives us the small probability. Okay? So I say that because often you see that you're trying to prove something, and you work and it doesn't work. And sometimes you just should step back and look at it and say, oh, it cannot work. What I'm trying to prove is just, it's not true. Okay? So a random variable, we expect it, if we have more and more observation, we expect the average to get closer and closer to the expectation. But it will never beat the expectation. Okay, and it's going to be somewhere, plus minus standard deviation, or 2 standard deviation. Okay, and here we got it here. Okay. So now let's do this comparison between the 3 bounds. Okay, so in order to get any strong results with a weak bound, we have to ask much, much weaker question. So let's ask, what's the probability that when I flip a coin n time, I get 3/4 heads? That's really unlikely. Okay, so if I plug it into the to Markov inequality, then the probability that I get 3/4 n heads, well, probability is bounded by the expectation times the value here, the A, and we get that the probability is just bounded by 2/3, which is really nothing. There's no bound here. In particular, what's really missing is that their intuition is that if we flip more and more coins, if we do more and more experiments, we expect it somehow to converge, to get closer and closer to the expectation. And here we get a bound that has nothing to do with the number of experiments we did. So that's Markov inequality. It's very weak. If we do Chebyshev, okay, so the probability that we deviate from the expectation by n over 4, okay, so now if you remember Chebyshev, we have to, that's bounded by the variance divided by this square. Okay, so the variance here is half time n, okay, and we divide it by this square, so we get n squared down here, and up here we cancel. So we get at least something that goes down to 0 with n, as n goes to infinity, but it goes down linearly with n, okay? So now we look at Chernoff bound, which we just proven. So the probability x deviates from expectation by n over 2. Okay, so that's probability that x is greater than its expectation 1 plus half, or it's smaller than its expectation by 1 minus half. Okay, so now we plug it here, and remember that the bound we prove is the expectation times the deviation square, okay? So the expectation here is n over 2, the deviation is half, so it's a quarter here. Then we have some coefficient here, okay? And what we get here is a bound that goes down to 0 exponential in n, okay? So going from one to the other, we started with a bound that doesn't even go down to 0 as n goes to infinity. Then Chebyshev gave us a bound that goes down to 0 as n goes to infinity, but it goes down as 1 over n, or inverse linear. And then we get a bound that goes down to 0 with n exponentially in n. Okay, so that's significant jump between these bounds. Okay, but the beauty is that they all build on the Markov inequality that is so weak on its own. Okay, so that's the basic bound, the Chernoff bound, and the comparison of the Chernoff bound. So that's, in particular, when you use it in algorithm, what does it say? It says that if I want to get something that is, exponentially small, or if I want to show that the algorithm, work fast, say with probability 1 over n, then I just need log n experiments, or log n values, instead of n values. Okay, that's a huge jump when you translate it to, execution of algorithms. We'll see example later. Okay, so the simple application of all this is estimating a parameter. And the question is actually not question probability, not question computer science, question in statistics, but it's give us the right idea of what's happening here. So, so assume that there is some p value unknown. So the story here is I want to know the fraction of the population that has a particular mutation. Okay. If I'm getting a sample from someone, a blood sample from someone, I can run a test and I can figure out if he or she has the mutation or not. Okay. Well, I could go and test all the population of India. This might take a long time. So the question is, how many samples I need in order to get a very good estimate for the whole population. Okay? And the same question, of course, is when you try to predict election results and all the other things. Okay. And of course, as most people other than scientists like you don't understand, is in order to estimate a value in a population, we actually don't care about the size of the population. The sample size, as we'll see, has nothing to do with the size of the population, which is always very surprising. So predicting the election result in India and in Singapore takes the same amount of the same 1,400 sample, assuming that you can get uniform samples or whatever. I know it's much more complicated than that. Okay, so we want to estimate a value that is unknown. So we are in what's called classic statistics. So P is some unknown, only God knows that. And it doesn't tell us, so we are only estimating it. We'll never actually know the real value. Okay? And we got to take n samples, and P tilde n will be the fraction of the samples that had what we're looking for, say the mutation. Okay? So given sufficient number of samples, we expect the value P to be in the neighborhood of our estimated value P tilde. Okay? Well, one way we can use the Chernoff bound is to estimate how close is P tilde to P. Okay? And as a function of the number of samples. Okay? In computer science, we usually refer to this as, and we often do it now in machine learning and stuff like that, we answer these kind of questions. And there are two ways to estimate a value, both in statistics and machine learning. One of them is what's called a point estimate, the other one is an interval estimate. Now, point estimate is very misleading because the point estimate is just a coincidence that your sample gives this particular value as a maximum, but the value can be in the neighborhood of this. In particular, if you think about okay. So a much more reliable, I don't want to get into this, it's like we can do it some other record, but much more reliable and meaningful estimate is what's called a confidence interval. So a confidence interval is, a confidence interval for a particular value t is I give you a range such that with very high probability, the value is inside that range. Okay? Now there's something very confusing here. T is this value that is written, God knows about it, but it's a fixed value. A random variable is in fact the interval, because the interval is what we get from our sample, the values that we get from the sample. Okay, so we say, well, if we got P tilde as our expectation of the sample, we go a delta plus and a delta minus, and we say, well, we expect the real value to be inside this interval. Okay, so this is actually the random variable. This is a fixed value in nature. Okay? Okay, so now we want to minimize. So the real trick here is you have these three parameters you want to play with. Okay, you want to minimize the interval so that you have a meaningful estimate. You want to minimize the error probability, that's Q. And you want to minimize the number of samples because that's what you pay for. Okay, that's what the work is. And so the question is, how do you get the trade-off between them? Okay, so you want the probability that the interval include the real value V, P, which is the same as the number of, positive observation you had minus delta plus delta. You want this interval to include n times P, and you want it to be with high probability. Okay. So we have to look at above that and below that, and I don't want to get to the detail of the calculation, but basically you get, you plug it into a Chernoff bound, and you get basically the relation between, you want this to be bounded by Q, you get N and delta here, so you get the full relation between these three parameters. So that's one simple application of a Chernoff bound that gives you very good values. And actually it gives you a very tight estimate. Okay? And again, we're playing with delta, with Q, with N. The size of population doesn't appear in this whole computation. Okay. Let me should finish soon, so let me just formulate a little bit what we said before, because again, this is important. So assume that we have, I just want to give you the more precise comparison between the Chernoff and the Chebyshev inequality. So assume that we have this, assume to make it easier that we just sum n random variables with probability P for success. There are 0, 1 random variables, probability P for success. So the expectation of the sum of n, this n 0, 1 random variable is np. The variance is npq. Okay, I'm sure you know all this. So if you do Chebyshev, you get the probability that you deviate from the expectation by delta times the expectation, okay, is bounded by the variance divided by the square of the deviation. And if you plug the right thing, you get that it's basically Q divided by delta square mu. And that's important. The important one is the delta square mu. And now if you do the Chernoff bound, okay, so the probability that you deviate by mu, okay, you deviate from mu by delta is bounded at e to the minus mu delta square over 3. So the delta square mu appear in both cases. It's the same one. Only here it appears as 1 over that. And here it's minus that in the exponent. Okay, so the real thing that go down to the real measure of convergence is in the expectation time the variation square, time the deviation square. Okay. Where is oh, your question, great. I don't hear you.
The Chernoff bounds are the best upper bound you can have, say, for coin flip experiment.
Okay, no. So, as usual, there's a trade-off between general tools and the best you can get. So, if you give me a particular problem, you know, I can probably squeeze somewhat better bound. Because to get the bounds, we did all sorts of simplification here. Yeah. But
for the example of coin flip, how can you improve?
For the example of the point estimate?
Coin flip, how the deviation from the expectation.
Yeah.
So you improve the Chernoff bound. But
Yeah.
you get a better upper bound using the specific information for the experiment.
Well, so depends what information you have, but you won't get much better. So we'll see next time that in fact the Chernoff bound for a very simple case of you know, two-value random variable converge. It looks very similar to actually the normal distribution. So beyond the fact that it's, you know, there's a question of convergence in normal distribution, we do it with respect to a particular n, we are getting very close to the limit. Okay? So, but again, when we developed the bound, we gave up we gave a little bit in getting the, you know, easier to work bounds. But the differences are not significant, so the exponent would not change. It's maybe some constants here and there. But, you know, asymptotic, that's the best you can get, at least for the case of 0, 1 random variable. Yeah. Say that again, I don't hear you.
Can you prove that this is sort of the best you can get in terms of asymptotics?
Again, so you can show it for the case of 0, 1 random variable. You can show that asymptotics you get very close to the normal, which is the limit. Not directly, but yeah, that's part of the reason. But again, so if you have n identically distributed random variables 0, 1, then yeah, then it converges. Then you basically show that you converge to a normal.
Using central.
Yeah, so you show that it's, so basically you get, in the limit you are in the optimal. But if you start with random variables that are different, then I don't think you can show directly that it's optimal. So there might be some tweaks that you can do if you use the particular distribution. But then, I mean, the whole idea of building this kind of tools is that you don't have to work, the details for each distribution, that you get something that works in general. Yeah. Yeah.
Based on this question, if we know, if we have some priors, then how can we use them to say something about those?
If we have a bias,
Priors. So,
Prior.
Prior.
or if you have prior. Okay, now you want to do Bayesian. Okay. Yeah, you can do that, but that requires some stronger tools. So, one way, okay, so keep your question for the next hour, I mean for tomorrow. So one way to look at bias is in terms of martingale. That's one way to look at it.